breaking the wall of surgical imaging, how AI is advancing real-time precision in medical procedures. Lena Maier-Hein, German Cancer Research Center.
On November the 9th, 1989, I was 9 years old. The fall of the Berlin Wall was important for me because my father's family was finally united again.
Statistically speaking, everyone in this room will undergo more than one endoscopic procedure for tumor screening, diagnosis, or therapy in the future. And if we don't advance the clinical state of the art, this is what could happen. In some cases, the tumor will not be detected, the cancer will spread. In other cases, vital structures will be injured. And in even further cases, the tumor will not be fully resected, leading to recurrence. With these words, I started a grant presentation pretty much exactly 10 years ago. I applied for 1.5 million euro from the European Research Council, ERC. But now let me start from the beginning. I'm Lena Maier-Hein. I'm a surgical data scientist. And I'm sorry, I will show you some bloody images now. So this is what a surgical team sees during surgery. And you see, you cannot barely differentiate anything from each other, right? So where's the tumor? Where are the nerves? Is the tissue well perfused? And already then, 2012, I was working based on such images. That was the input to our algorithms. And when I listened to the device manufacturers, they talked about higher resolution, 3D, such aspects. And I was wondering, is this really what we need? And I have to tell you, at that time, I was doing my postdoc with Dan Elson from Imperial College London. I was pregnant, I didn't have a permanent contract, and I was questioning everything my whole scientific life. And I kept on thinking about Henry Ford. It took me ages to generate this picture, but this is a different story with AI. If I had asked people what they wanted, they would have said faster horses. And here, the faster is the ever-increasing resolution. So what is the car? Okay, let's recap some camera technology first. Maybe not everybody is familiar. I went to Morocco last month, actually, and I visited the famous garden Yves Saint Laurent. And I was so disappointed when I saw the images that they had put up for their 100th anniversary. Why? Because they were missing the colors. I mean, look at the difference, right? It's dramatic. So what does it mean technically? I'm sure many of you are familiar with the traditional camera model, which gives you basically grayscale, black and white images. This camera model basically captures the intensity of light, one value per pixel. Now, you may know that our eye is sensitive to red, green, and blue, so the modern cameras are based on human perception. They imitate human perception by separately filtering red, green, and blue light. So now you have 3 values per pixel. But also you can imagine that the human eye, from an evolutionary perspective, right, it was optimized for natural environments and not for performing surgery. So again, a bloody image, sorry. But here you want to remove the tumor, and then the outcome depends crucially on whether, after the surgery, the organ is well perfused or not. Red in this animation or blue. But this is very, very hard to tell from these images because everything just appears pinkish, reddish, right? So now let's finally talk about the car. So here, in this graphic, you see the main absorbers of light in tissue. So you can forget about melanin, a strong absorber, but it's mainly contained in the skin. And this leaves us with hemoglobin, Hb, bound to oxygen or not, as a very strong absorber of light. And what you will also note, and this is actually the key observation, is that all these molecules absorb light very characteristically, right? You have very different curves. So the hope was that now, by basically acquiring many different images corresponding to the different frequencies of light, we can potentially reconstruct the molecular tissue composition and recover important clinical information such as the tissue oxygenation. And this is exactly, coming back to the beginning, what I pitched the ERC, 10 years ago now. So I wanted to revolutionize surgical imaging by leveraging the potential of biophotonics, that's the field of light-tissue interaction, with AI. So long story short, and this is really how I felt, I got the money. But then the trouble actually only started. Because we couldn't just purchase the equipment, and I mean, I'm a computer scientist, I'm not a hardware person, but we couldn't purchase the equipment that we needed to acquire such images in real time, and maybe even more importantly, in patients. So we had to overcome a lot of regulatory and technical hurdles in order to build such a system ourselves. So again, I'm making a long story short. I don't have time to go into technical details. But what you can remember now is that in each pixel, we get a whole range of values. So whatever we acquire with this camera is per se not longer human interpretable. And this leads me to the final, the algorithmic challenge. So how do we convert this high-dimensional data that we now have to the clinically useful information, such as the oxygenation in the tissue? So because we have real-time data, the data is very noisy. So you cannot, apply traditional model-based techniques that use first or second order derivatives, etc. So the natural choice for me as somebody trained on AI was AI. So why had nobody ever explored the AI route here? Because we have a hen-egg problem. So if you think about it, we want to train our algorithm to recover the clinically important information from the spectral images. This means we have to show our algorithms training data, right? Pairs of the spectral data and the corresponding information. But for that, we need a device that gives us the information, which is what we want to build in the first place, right? This is why we're doing the whole project. So really, you could say this is a true roadblocker. So what could we do? And at that time, maybe it doesn't sound controversial now, but it was really controversial 10 years ago, we decided to go for synthetic data. So we built a digital twin of our device. We used all our knowledge on how tissue is composed, how light interacts with tissue, how light interacts with cameras, to build pairs of plausible tissue configurations and the corresponding data that we would expect. And we built this in a way, the algorithm, that it can automatically adapt to tissue. And maybe you don't believe me, and this is why I brought my great team members, Leo, who did his whole PhD on this, and Michael, who is now exploring.
Thank you for the introduction, Lena. So Mike and I today, we're going to talk to you about the system that we built, which is what Lena was just talking about. And when we first started designing this system, we wanted to build something that is easy to use in the clinics. And for that, we had to weigh different features of this system, such as, for example, the speed, resolution, and weight of the system. In the end, we decided to prioritize speed because this is such an important feature during surgery. And we decided to overcome all the challenges through AI methods. Unfortunately, we cannot go into details about how these methods actually work, but if you're interested, you can approach us afterwards, and we can tell you more about it.
So this little black cube, that's a spectral camera. And this is the laparoscope, which is the part that goes into the patient's body during minimally invasive surgery. We don't want to perform a real-time surgery on stage today, so I'm going to show you on the skin. If I hold my hand below here, you can see on the right side the RGB image of my hand. And on the left side, you can see the output of the algorithm. Now, it apparently does not work. It works when you're nervous as well, so that's good. So what you can see is that this finger here is much bluer than the other ones. Blue here means that there's low blood in my finger, and red means that there's a lot of blood in my finger. So my finger is blue because I clamped it like 2 slides ago. So if we release the clamp now, you should see blood coming into my finger because my body reperfuses it.
Another very important feature of this system is that it can actually generalize to other people. And if you don't believe me, for the skepticals out there, I can show you on my hand. So if I place it underneath the camera, so you can see, as Mike just mentioned, red means a lot of blood, blue means less blood. And now if I, for example, rub my finger over my hand, what I'm effectively doing is just pushing the blood out of my hand. And if I stop doing that, you can see that it quickly reperfuses because it turns red back. Once more. This can also generalize to other parts of the body, like, for example, internal organs, and Lena will tell you more about this.
Yeah, so you saw the system applied to the skin now. Our first application was actually kidney surgery. This was in collaboration with the great Dogu Teba. And the snippet I selected here actually shows you, and this was the very first patient, a very exciting moment for us. It shows you also how the tissue is quickly reperfused after we release the clamp. So you put the clamp in the surgery such that basically you can remove a tumor without excessive bleeding. And since then, we started to explore a lot of different options. I'm very grateful to the great team of collaborators that we're working with, from visceral surgery to neurosurgery, anesthesia. And for example, this is an example where we monitor the oxygen consumption in the brain. It's a fast-forwarded movie to develop, this is an ongoing project, medication against stroke. This is also in case some of you has a migraine. This is also how your brain looks when you have a migraine. We also look into optimization of surgical techniques, because now we have an entirely new window into the body, right? We look into fully automatic tissue differentiation, not only for pathologies, but also for full surgical scene understanding, and then eventually surgical autonomous robotics. And we assist in different surgeries. We do perfusion monitoring, for example, in organ transplantation. But I want to close with a recent highlight that is unpublished. I wanted to tell you something new. So you may remember this figure here. And so far, I talked mainly about perfusion monitoring. And in this area, basically, you can work with a visible light, where hemoglobin is the primary absorber. Now, let's move to the invisible, to the near-infrared light and beyond. So there you see that water also becomes a strong absorber. And our collaborators had a very interesting idea, Professor Weigand, Professor Dietrich. So you may know that sepsis is actually a very, very severe condition, blood poisoning. So statistically speaking, again, while I have been giving this talk, dozens of people died of sepsis. And the hypothesis was that the micro alterations caused by sepsis is something that we can measure, and that specifically also leads to water concentration changes. So what we did, I'm not going to talk about the hurdles now, but what we did was we took measurements of the palm of all the ICU intensive care unit patients in the university clinic in a certain period of time. Okay. They told me I should go over time so that you can finally see the artist that chases you away. So long story short, we found a new biomarker for sepsis, and I'm very excited about this. And now I will go over these 50 minutes on purpose, because the artist should go on stage. So I talked only about visual sensing, but surgery is so much more. It's about palpation. It's about... Are you the artist? It's about acoustic signals. It's about team dynamics, and we have to go all the way. I promised I would go a little bit over time and introduce already the next talk from AI to AGI.